All right, so welcome to this quarter's Astrobiology seminars. Today's speaker is Hilke Schlichting. She's an associate professor at UCLA. She did a PhD in astrophysics at Caltech. That was 2009. Then she did a postdoc at UCLA. Then she was junior faculty at MIT. And then I guess she loved UCLA so much she went back there, which is where she is now. And her interests include things like impacts on planets and how that affects atmospheres, the formation of planets, including the kind of things that we see in other solar systems, such as super-Earths, and also orbital dynamics. And today she's going to talk about atmospheric accretion, evolution, and loss of super-Earths, sub-Neptunes, and terrestrial planets. So I think that covers quite a bit of ground there. So let's go ahead.
Well, I did put it on. There you go. Can you hear me? Yes. Well, thank you very much for the nice introduction. Yes, you are correct. I have a little bit of an ambitious program for today, but, you know, I think we can do it. But if you don't get to the very end, that's fine too. And I'd much rather have you ask questions. So if I say anything that doesn't make any sense to you, or if I generally confused you, or if you have any other questions, please feel free to ask, because I'd much rather have you understand what I'm trying to say than cover every single slide in my talk. So with that, let's start. So usually I used to start my talks by giving an overview about planet formation and how we think our solar system formed. But I decided for today that maybe it's time to do the opposite approach. Actually, I'm going to start with telling you about what we learned from other planetary systems, with a focus on the large number of exoplanets that have been discovered by Kepler. And I will tell you what we learned about their formation and their physical properties, and then I'll go back and basically speculate how our own solar system fits into what we learned from that. So as some of you know, or maybe all of you know, the Kepler mission was looking for planets around other stars using the transit method. So when another planet blocks out some of the light, and it's been a huge success. It was much more successful than we had anticipated, because nature gave us all these planets or planetary systems that we actually did not know existed and that are very different from the ones in our own solar system. So what I'm showing you on this plot here is the size of a planet in Earth radii as a function of period on the x-axis. And every single blue point corresponds to one of the planets discovered by Kepler. And these green points here are actually Mercury, Venus, and Earth from our solar system. So I like this plot because what it shows you is that there are many other planetary systems out there. In fact, these sort of planets that are typically in size between Earth and Neptune are currently the most abundant planets known in our galaxy. And at least every other star seems to have one of those guys around it. And what is so surprising is that live in an orbital period space where basically our solar system is empty, right? Most of them are within sort of 100 days period, and we don't have a single planet. So what's intriguing is that we don't have a single one of those planets between the size of Earth and Neptune, and also not in this period space. And so the question is, how do these planets fit in with what we know about planet formation? And how should we think about their formation? You know, should we think of these guys as super-Earths, like upscale versions of the terrestrial planets that form just a little bit bigger? Or, you know, maybe they form much further away, and they form maybe more similar to Uranus and Neptune as ice giants, and then maybe they migrated to their current locations. Or maybe life is even more complicated than that. So that's my super-Earth. Here's my mini Neptune. that's sort of the question that we'd like to answer. We know a little bit more about these planets rather than only their radius and their period, at least for a fraction of those. We know their masses, and given their masses, in many cases, we can infer that they must have some light gas, most likely hydrogen helium, on top of that, typically between 1 and 10%, to explain the large radii that we see from them, given their mass. So you could not just explain them with sort of rocky or water composition. And then this result has been firmed up further. So here's a plot that shows sort of the average planet density as a function of size. And you see that the density sort of increases with planetary radius, as expected because of self-compression, up to sort of 1.6 Earth radii, and then it sort of goes down. And again, it seems to suggest that there are these two populations. So planets that are less than roughly 1.6 Earth radii are planets that look like terrestrial-type densities and compositions, and planets bigger than that look like they have significant hydrogen-helium envelopes, about 1% or more in mass. And then even more recently, this plot here as a function of orbital period has been produced. So now this is showing you planet size and Earth radii as a function of orbital period. And these two islands emerge. Again, where the planets on the top island correspond to planets with hydrogen-helium envelopes, most likely, and the ones on the bottom island look like basically rocky-type cores. And then people went through some great effort and actually measure the slope that goes in between those two islands, but we're going to come back to this later. But all these observations basically got us thinking of how we should think about the formation of these planets. Specifically, should we think of these planets having formed as one population, and then somehow it evolved into these two different paths, we have a bimodal outcome, or do we really have two populations, having a population that formed analogous to the terrestrial planets as rocky material, and a population that really formed more analogous, say, to Uranus and Neptune? And so to answer this question, we started thinking about physically, how does the gas accretion for these planets work? How much of this gas that you would accrete will you keep, so you can see it today? And what sort of loss mechanisms are likely at play that will shape this population, just from a planet formation point of view. And so you may wonder, why do I care? Especially if I care about planet habitability. What do I care how these things formed, as long as they're rocky at the end? Maybe I just don't care. And I think why at least I care, I don't know if this will convince you, is even those guys down here that look like rocky composition cores, they could potentially have small hydrogen-helium envelopes today, and I think that would have interesting implications for both whether or not you can have outgassing, what sort of compositional atmosphere you have, and then if they are located in the right phase space, what sort of life would likely exist on those planets. Okay, so let's think about gas accretion. Let's assume we are able to build up our planetary core. So when you're building up a planetary core, initially, your cores are so small that you can actually not have an atmosphere. You cannot hold on to an atmosphere. How small is too small? You have to be smaller than what we call the Bondi radius. What is the Bondi radius? The Bondi radius is just the radius of an object up to which you can have an atmosphere. So basically, it's the distance where, given where you are from the star, the thermal energy of, say, the gas molecules you have is equal to the escape velocity from the body. So, and the interesting thing is, if you're too close or too small, then actually the thermal equilibrium temperature you would have, your gas would have from the star, is actually so high that, say, an asteroidal-sized body could actually not hold on to an atmosphere. At 1 AU, you have to be a little bigger than Ceres, roughly, to actually have a Bondi radius larger than your physical radius. So first of all, you need to be big enough. So this is why asteroids don't have atmospheres to first order. Okay, so you're forming a planet. So initially, in the gas disk, you don't care much that the gas is there, at least not in terms of your atmosphere, because you can't hold on to any of it gravitationally. But eventually, you grow to sizes large enough such that your Bondi radius becomes bigger than your physical radius of your growing core. And now, gravitationally, you can hold on to an atmosphere. So the initial atmosphere you have is basically just the gas that's inside your Bondi radius. So this is great, but that's not enough to actually start having significant gaseous envelopes. What then happens next is your core keeps growing, and your gas that you're accreting will start to cool, so the atmosphere will shrink, and you can actually accrete even more gas. One important point here is that the temperatures of these cores are really, really hot. They are between 10 to the 4 to 10 to the 5 Kelvin for planets that are in mass between Earth and Neptune. And the reason why they are so hot is because as the cores are accumulating, they need to get rid of all this gravitational binding energy. And as long as you don't have an atmosphere, that's no problem, because the gas will just carry away that heat as it's flowing by. But once you start building up an atmosphere, and this atmosphere will become optically thick, it acts like a thermal blanket, and it's keeping that heat from formation basically in the core. So these cores that sit under these hydrogen-helium envelopes are pretty hot, roughly 10 to the 4 to 10 to the 5 Kelvin. You know they can't be hotter than this, because if you make the cores even hotter, you would basically unbind the envelope. So the cores are sort of the maximum temperature they can be while still having this atmosphere. OK, so this is our initial condition. And then you can ask, OK, so how does my gas accretion work? What's going to happen next? So the first thing will happen after I just count up the gas that's in my Bondi radius, which is about 0.1% of my planet's mass. It will start to cool. So the envelope will start to cool and shrink. And now I can add on more material from the gas disk. And so I'm accreting. The structure of my atmosphere at this point is basically the inner regions, which are most of it, actually. They extend almost all the way to the Bondi radius. Basically, heat transport is mostly by convection, so their profile is close to adiabatic. And then you get a very small, almost isothermal outer region where you basically have radiative heat transport. So in this way, you start accreting your atmosphere. Because you basically have to cool and shrink to basically be able to accrete more material on the outside, how much of an atmosphere you accrete actually depends not so much on the gas density in your disk, but it depends on how much time you had to cool. Because the more time I give you to cool, the more time, the more my atmosphere will shrink, and the more gas I can pile on from the outside. So if you then calculate the ratio of the atmosphere accreted, so of my hydrogen-helium atmosphere accreted, compared to the mass of the planet, so this is F, this is the ratio of the atmosphere to the core, what you get is it's about 2%, and then it scales as the planet's mass, right? Because the bigger the mass, the bigger is the Bondi radius. Then the equilibrium temperature, and just right, because again, it tells you to what distance my molecules can be bound. And then what matters is the disk lifetime, because it tells you how much time I have to cool. If I make this longer, I can accrete more material. And then the opacity, because the opacity regulates how fast my envelope can cool and contract, so I can accrete more. And specifically, it's the opacity at the radiative-convective boundary that's really the important one, because this is the bottleneck, if you wish, where the heat can escape from the inner parts of your envelope. So what is nice about this is that how much atmosphere you accrete does not really depend on the gas density in the disk. Or it does, but only logarithmically. And it's logarithmic because the isothermal part of your atmosphere, right, has an exponential profile. And so this is why you get a logarithmic term in the density. OK, so shall we declare victory? We accreted a few percent of hydrogen-helium in typical disk lifetimes of a few million years. That's sort of all I need to explain my observations, right? So we are good. Or at least some people thought we were good. I think we're partly good. So this is a great step in the right direction. We can definitely accrete enough envelopes to sort of explain the typical observations. I think, by the way, this also explains why gas giants are so much rarer than super-Earth and sub-Neptunes. Because to form a gas giant, you need to go through this phase and then enter runaway gas accretion. But to enter runaway gas accretion, right, the envelope fraction you need to accrete needs to be, let's say, 20% or so, at least. And so you can see that this just takes a long time. So just increasing the density in your disk doesn't help. It just takes a long time. And we know that most disks don't stay around more than 10 million years. So I think it's a nice sort of intuitive way to understand why you occasionally get gas giants, but why typically a Neptune is a much more common planet. Or Neptune, I mean a planet with a few percent atmosphere, is much, much more common than a Jupiter. I think it's to first order just the disk lifetime. And the fact that this sort of hydrodynamic accretion, if you wish, is relatively slow. Okay, so we can't yet quite declare victory. And the reason for that is that we actually do not get to keep all the atmosphere we just accreted. So why is that? It's because when the gas goes away, it actually takes some of it with it. And so what is happening here is the following. As the gas dissipates, you basically lose pressure support right on the outer edge of your planet, if you wish, at the Bondi radius. And if you lose the pressure support there, what your gas will want to do is wants to adiabatically expand into vacuum or in the lower density surrounding region. And your envelope has plenty of energy to fuel this expansion. Because right, when you expand adiabatically, you cool, but you have plenty of energy, thermal energy in your envelope that can be supplied to sustain this expansion. And as a result, on the same time scale on which the disk goes away, your planets actually tend to lose 25 to 70% of the envelopes you just accreted. The exact number actually depends on the adiabatic index of your envelope because that determines how the mass is distributed inside it, but it doesn't matter so much. So let's say 50% is what you lose during the disk dispersal time phase. So it's okay, but just remember, if you want to form your planet, make sure you accrete at least sort of a factor of 2 more in gas that you want to have today because of this. The other consequence of this is because you're losing this material and basically you're providing energy from the interior of the envelope for this adiabatic expansion, the remaining atmosphere and the radiative-convective boundary, for what all practical purposes can be thought of as our size or edge of our planet, is that okay?
Don't worry about that.
Okay. I shall not worry. You don't seem worried. I won't be worried. So basically, the remaining envelope will shrink rather rapidly. So it's basically, by removing material, you were able to take away energy quickly. And so your planet will actually shrink to sort of a size, or the envelope to a size that's comparable to the core radius. So this is really interesting. So on the time scale sort of on which the disk goes away, which say is a few million, maybe 10 million years, your planet would not only shed roughly half of the mass it accretes, but it actually will also shrink in size significantly to a few times the core radius.
What's the capital R, RCB?
Yeah, so the RCB is the radiative-convective boundary. So thank you for asking. So the structure of my envelope is the following. So on the inside, heat is transported predominantly by convection, so you get sort of an adiabatic profile. But then that transitions at the radiative-convective boundary to an isothermal profile, or close to isothermal profile, where heat transport is done mostly by radiation. This is like a very simple model. If you do really complicated opacities, this will be much more complicated. But it's just like the zero-order, simplest astronomer's atmospheric model for your planet.
And the gamma is the ratio of specific heats.
Exactly, and the gamma is the ratio of specific heats, and that depends on whether you have diatomic or monatomic, or even, if you have ionization of some sort, it can be. So you can choose, or you can even have this transition inside your envelope if you do very careful models. But this is to give you a feel sort of on what to expect. And actually, that's maybe a good point to make here is you'll see this is sort of, what I'll tell you mostly focuses on understanding the key physics that's going to happen. People have actually studied at least parts of the things I'm talking about in great detail, but the thing that had been lost so far is tying these together. And for example, this mass loss phase has been entirely missed because people went from worrying about atmospheric accretion to just thermal evolution models that follows the shrinking of the envelope you have accreted, sort of missing what happens during the gas dispersal phase. So I think the value in most of what I'm going to tell you today is trying to have a self-consistent model, tying these different stages together and see what the consequences are. And then there are definitely many parts that are definitely worthwhile to study in a lot more detail. But that's sort of the broad picture idea here. Okay. So, and then this would be the true initial condition. If you want to do thermal evolution models of these planetary atmospheres, how they shrink in time, this would be your realistic initial condition. And this is very different when people usually just start with arbitrary large atmospheric sizes or unknown entropy in these envelopes. I think we can actually make at least a very well-informed guess of this initial condition. So what happens next is even more interesting. So now we accreted our atmosphere, the gas disk is gone. And now what happens to your planet, or at least its envelope, actually there are two different outcomes. It has two different paths and can follow. And so there are two actually quite different cooling regimes. So in the first case, I call this sort of the heavy envelopes, in which case the heat capacity of your system, or the energy available for cooling and for being lost from the system, is dominated by the atmosphere. Now, your planet will just cool and contract in time. So if you follow the radius of your planet in time, you will just see it cools and contracts over gigayear timescales. And this is something that people had studied for a long time, just by itself. So when you think about the atmosphere, what happens is, here's the inner adiabatic region, here's the isothermal profile, here's the radius of your atmosphere. With time, the radiative-convective boundary will move in, it will shrink, and the density at the base of your atmosphere, where it's connected to the core, will go up. And this will just continue over very long time scales. Right, we know today Jupiter is still losing heat, or is giving away more heat than it receives. So this cooling time scale can take easily gigayears. So this part is fine. There's not that much new here. The other case is actually more surprising or more interesting. So if the energy available for cooling, or the heat capacity of your system, is dominated by the core, you get a very different outcome. So now, my planet still wants to lose its heat, right? My atmosphere still wants to cool and shrink. However, as my atmosphere is trying to do that, basically the energy that's being lost or radiated away or diffused to the radiative-convective boundary is being resupplied by the core. So the atmosphere and the core are very well coupled, because you still have these incredibly high temperatures of 10 to the 4 to 10 to the 5 Kelvin. So the atmosphere and the core are sort of acting as one system, cooling together. And so as the atmosphere is trying to cool, basically most of that heat is being resupplied by the core. And by core, I mean just the rocky part of the planet. The rocky is the astrophysicist's core. So if you're an earth scientist, I mean the rock, the crust, and the iron core. If you're an astronomer, I just mean the core. So it's being resupplied. And so instead of my planet being able to shrink and contract its atmosphere, the atmosphere will just stay constant. It cannot shrink. And you continue to lose mass. So mass loss happens, it's almost like a Parker-type wind. So you basically have your profile extending all the way to the Bondi radius, and the mass loss rate is dictated by the escape rate of your molecules from the Bondi radius. And this will continue. This can actually lead to complete atmospheric loss, because there's plenty of energy. From an energy point of view, there's plenty of energy to do the job. And this process is a runaway process, because once, at least energetically, you've lost half your envelope, losing the second half is even easier. So if you look at the profile, what it will do to first order is the following. You cannot shrink in radius So instead, what happens is you drain mass. Mass is lost out here. And so the density, if you wish, of the envelope and the core intersection, or at the bottom of your atmosphere, the density there will just shrink in time. And this way, at least energetically, you can lose your entire atmosphere. There are two things that can save you. In this case, it can be that the actual mass loss will take longer than the age of the system. And the reason why this can take a long time scale is because the Bondi mass loss rate has an exponential in it because of this isothermal layer here, or the radiative part, which is close to isothermal, so you get like an exponential in the density profile. And so if you are far away from the star, this can start to take a long time. And it can take, gigayears. So there could be cases where this is actually still happening, and so you haven't lost everything. And there is a second case where you can save some of the atmosphere, and that's when you can start cooling faster than you lose mass. Because once you can start cooling faster than you're losing mass, you can shrink your envelope, and then you cut off any additional mass loss, again, because you have this exponential tail. And so it's very sensitive to shrinking, basically, your radiative-convective boundary, the size of your planet. OK, so let me just try to summarize this very quickly. So once your gas disk is gone, in whatever envelope you have left, there are two different paths of evolution. In the first case, the energy available for cooling is dominated by the envelope. These are heavy atmospheres. Oh yeah, I forgot to say, for practical purposes, what's a heavy envelope? When is the heat capacity of your system dominated by the atmosphere? It's for cases where the atmosphere, if your hydrogen-helium atmosphere, have more than 5% of the total mass. And so this is, to first order, just the ratio of the mean molecular weights between your envelope and the core. In those cases, you don't have enough energy to unburn these remaining envelopes, and they will just shrink and contract in time over gigayear timescales. If the cooling energy is dominated by the cores, and this is what I call light envelopes, which will apply for planets that accrete at less than roughly 5% of the total mass. Here I have 5 and there I have 10, there you go. Anyways, in that case, you can energetically strip the entire core and have no hydrogen-helium left, unless the mass loss time scale becomes longer than the cooling time scale or the age of the system. But what this means is that planet formation itself sort of predicts a bimodal outcome for these planets that had hydrogen-helium envelopes of a few percent. And it's somebody calling me? And it really is a bimodal outcome because, as I said, this mass loss is a runaway process. So if you can do half, you can do the second half even more easily, so you tend to have very few that are sort of in between. So one last thing before I can show you some results. What do these cooling time scales look like? And the mass loss time scale or the cooling time scale, right? It's just the energy of your system divided by the rate at which you lose this energy, which is basically the luminosity at the radiative-convective boundary. So it's basically the rate at which you can diffuse through that boundary and then be radiated away. The mass loss time scale is simply the mass of your atmosphere divided by the mass loss at the Bondi radius. So what is that? Well, if the Bondi radius is a sphere, we get 4 pi the Bondi radius squared, right? Times the density at the Bondi radius times the speed of sound. And the density of the Bondi radius, this is where the exponential comes in, because the density at the Bondi radius is connected to the density at the radiative-convective boundary to first order by an exponential profile, because this is close to an isothermal atmosphere. OK. So with this in mind, we can now see what we would predict from this for a population of planets that have masses basically consistent with observations on sizes between, say, 1 and 4 Earth radii. So what you do, you use the observed distribution of exoplanet masses. It's not super well constrained, but reasonably well enough. You then know, so once I give you the planet masses, I know the orbital periods, or actually the equilibrium temperatures from the host stars. So I can then, I know from the work I did on the accretion, how much of an envelope fraction they accrete. So I just calculate that. Then I know how much they're left with after the disk has gone away. And then I just have to follow the thermal evolution of this population and see what I'm left with. And this is exactly what Sivan did in this figure here. So he followed this through and basically came up with this following occurrence rate. So what I'm showing you here is planet size, again in Earth radii, and the relative occurrence. So his results is this red line. And you can see, as expected, you really do have a bimodal distribution. And then in gray with the arrow bars, which probably you can't see super well at the very back, these are the observations. So you can, so the upshot of the take-home message was actually that you can really reproduce the observed radius distribution by accretion and basically following this core-powered mass loss alone. So just sort of as a byproduct of planet formation. So you do not need photoevaporation to produce this bimodal outcome. I'm not saying photoevaporation is never important or never happens, but what I'm showing you is just as a byproduct of planet formation, you would actually expect having this sort of bimodal distribution. And then my current grad student improved on this a little bit more because there are more observations available, so we can do more detailed comparisons. And so what he did is he extended this. So this was just a simple histogram, right? Relative occurrence rate is a function of planet size. There are enough exoplanets now that people were able to make a plot in 2 dimensions if you wish. So this is orbital period. The observations here are just orbital period and planet size. And again, you can see these two islands I showed you before. And if you look in this period space, we get very similar results. Again, you see these two islands of the hydrogen helium-rich sub-Neptunes, and then these sort of almost barren or barren rocky cores, which we call the super-Earths. What we find is, in most cases, what really sets the slope of this valley is actually that the cooling time scale eventually becomes shorter than the mass loss time scale. And then you shut off any further mass loss. And so we can actually predict both the slope, where the slope should be, and the gradient of the slope by simply equating these two timescales, the cooling timescale and the mass loss timescale. And in reality, they're a little bit complicated because they depend on many things. However, in practice, because, as I told you, the mass loss timescale has this exponent in it, or this exponential in it, everything that's not in the exponential doesn't matter to first order. So all you really have to worry about is what's in the exponent. And this is what's written in the exponent. Actually, here, this is the full exponent. This is just the Bondi radius of your planet, or very similar to that. So that's all that matters. It's the mass of the planet, the speed of sound, and basically the size. And so what you can do, and this is basically constant when these two become equal. So we can then solve for this, because we know what all these things depend on. The only assumption we have to make is it depends on the bulk density of your core, which sort of is a free parameter, and on the mass-radius relationship of your planet. So if you have a planet a certain mass, how does the radius scale with the planet? People had predicted from both experiments and theory it should be close to the 4th power because of self-compression of these larger cores. And so if you assume this, you find that the slope in this parameter space should be minus 0.11. And this is actually in very good agreement with observations. So we can now, of course, turn this around and say, yes, indeed, using a mass-radius relationship that accounts for self-compression where the planet mass goes as the radius to the 4th power, is indeed needed to explain these observations. If you do this to the third power, it won't fit. So you can basically see that this highlights sort of the importance of subcompression in these cores. This is not a big surprise. People sort of predicted this 10 years ago, but it's nice that you can actually sort of confirm that observationally. What else can you do? I told you it depends on density. So we just assumed an Earth-like density when we made this first figure. But of course, that was just some biased assumption of mine, or maybe of my grad student. So instead, you can ask, what would this look like if you had cores that were entirely made of ice or entirely made of iron, just like as extreme end-member cases? And you can see you still get these two peaks, but the location of your valley will move. In fact, it will move up for icy cores because the location scales as the density to the minus 4/9, and it will move down for iron cores. So again, you can turn this around and say, given that I have to match the observations, how much, for example, water could I hide in these planets if I assume Earth-like composition? And the answer is at most about 20%. So if these have typical Earth-like compositions, they could have up to 20% by mass in water, but not more. So this is interesting because what this tells us is that these planets probably formed inside the ice line, or at least in sort of a water-poor environment. So this is pretty exciting. So it looks like on average, statistically speaking, these planets do have compositions similar to the rocky planets. Unfortunately, all we ever get to really know this way is the bulk, the average density, right? I can't tell you how we divide this up between iron and silicates and I don't know what. So it would be great to know a little bit more how similar they really are to, say, the Earth. And so this is a very small aside, but I thought it's sort of nice. We're starting to be able to actually say something about sort of the geochemistry or how geophysically similar some of these extrasolar rocks are or can be. And this is a plot from a paper that was recently submitted by another grad student at UCLA, Ellie Doyle. And what she did is she used polluted white dwarfs. So why are they useful? So in polluted white dwarfs, we can basically probe the composition of the material that's being accreted. And it has been shown in the past, it always looks distinctly rocky, very similar in composition to like sort of the bulk terrestrial planets or the asteroid belt. But she took this one step further, and she basically used that to calculate what the geochemists love to call the oxygen fugacities. If you don't know what that means, don't worry. Basically, it's basically probing sort of how oxidizing your planet is, or basically how much iron oxide you have compared to iron. So how much of a core you have compared to not a core and the iron being just existing as iron oxide in your planet. Why do you care? We care because it plays a role in determining the planet's structure and sort of, for example, how heat can convect in the core and the mantle. So it matters for the evolution of the planet. It will matter what sort of atmosphere and outgassing you can get. And what she finds is that for this rocky material that's been accreted, it has actually values of this fugacity, so of how oxidizing this rocky material is, or these conditions are, very similar to the terrestrial planet. So there's Earth and Mars, and then some carbonaceous chondrites, and her white dwarfs, 5 out of the 6, are basically the same value. So what this suggests is actually that at least some of this rocky exoplanet, this rocky material that is accreted outside of our solar system, looks geophysically and geochemically very similar to that what we have on Earth. And it suggests that processes that led to the oxidization of rocks in our solar system, although we argue about the exact details of these processes, appear to be typical in other planetary systems, in the cases where we can sort of try to probe this. So I think it's cute. We're starting to not only say that the cores look like consistent with rocky densities, but the few extra tests we can start to do seem to be consistent also in terms of sort of the geochemistry. Okay, so I think it's a good time here to briefly summarize what I told you so far. So when we try to understand atmospheric accretion, we find that accreting 1 to 10% of cores that are sort of between Earth and Neptune and mass over typical disk lifetime scales is no problem. So that's great. You should make sure you accrete a little extra than what you need, because as the gas disk goes away, those planets tend to shed roughly half of what they accreted. And as a result, those atmospheres shrink to reasonably small sizes on sort of 10 million year timescales. From then on, there are two different paths your evolution can take. If most of the energy available for cooling is dominated by the envelope, then your planet can just shrink and contract, as we sort of used to thinking about. If, however, the energy available for cooling or the heat capacity is dominated by the core, then actually the core has enough energy that it can unbind over time the entire envelope on top. And as a result of this, you can actually produce, by what we call core cooling alone, the observed value of this bimodal distribution in the exoplanet sizes. If we then use that to further learn something about the exoplanet population, we find that it really shows that you have, from the mass-radius relationship, core compression in these cores, which again is not a big surprise, but it's actually really nice to see that observationally. And from the bulk densities, that the typical compositions seem very similar to the rocky planets that we have in the solar system, and that at most, on average, we can hide about 20% of water in these cores, which suggests that they probably formed in an ice-poor environment, or you lost all the water afterwards. And that at least some of the rocky exoplanets or extrasolar rocks appear to be geophysically and geochemically similar to Earth. You still with me? Yeah, I have a little bit more. Okay, so how about a few more tests, a few more thoughts? So very briefly, what I showed you so far, we assumed we only had sun-like stars. But of course, we know that Kepler not only had stars that were identical to our sun, so we can actually do a little bit better in terms of modeling this core-powered mass loss by including the true distribution of their stellar properties. And this is what Akash did here. And what you see is that to first order, things are not drastically different, but basically his results from here changed to these. So you can see they're a little bit smeared out as expected because you have a bigger range in effective temperatures and so on. And it actually gives an even better match to the observations if you really care about comparing things at that level of detail. So one thing that is interesting, and I'm telling you about this because I'm always asked about photoevaporation, is the dependence of the core-powered mass loss mechanism on stellar mass. So for the core-powered mass loss mechanism, the only thing that matters is the bolometric luminosity of the star. And why does it matter? It's because it sets the outer boundary condition of your problem, right? It determines where the Bondi radius is. And basically, it sets the temperature there. And so if you have a larger bolometric luminosity, you can strip more massive cores. So this is why in the core-powered mass loss mechanism, you expect, if you plot where you separate your sub-Neptunes from your stripped cores, you'd expect this to move to larger planet sizes as you go to more massive stars, because more massive stars have a larger bolometric luminosity. The scaling goes roughly as luminosity scales like mass to the fourth. And this is indeed what we find when you do this in a numerical model. But you can, again, just get it simply from this expression here. What's in the exponent, the only thing what depends here for us is the speed of sound, which is set by the effective temperature or the equilibrium temperature, right? And therefore, you can solve for what the slope should be, and we'll find analytically it should be roughly 0.28. Numerically, I think we find it's 0.3. It's basically the same thing for all practical purposes, given the crudeness of everything. So this is what we predict and what we find numerically. What do people find observationally? These are the observational results. And again, I would say it was a surprisingly good agreement. So observationally also, you find that the gap moves to larger planet sizes as you go around more massive stars. Fine. So how does this compare contrast if you would assume that it's photo-operation that's giving you this bimodal distribution? So photo-operation, to first order, would predict no trend at all. So photo-operation, right, it's actually the low-mass stars that are more active, right? It's the low-mass stars that give you all the XUV and X-ray radiation. Or specifically, it's the low-mass stars that have a stronger XUV radiation compared to the luminosity. So if you only model this with photo-operation, you would expect no trend in this with stellar mass. And people who have then done that have interpreted, have tried to match the observations. And the way they've been able to match the observations is by saying that the underlying distribution of planet masses must change as you go from lower mass stars to higher mass stars to explain this trend. So we would say there's no change. If you go from 0.8 to 1.2 solar mass stars, the underlying masses of your cores are roughly all the same. And this is something you can just check observationally. So let me summarize this. So the core cooling, the mass loss due to core cooling only depends on the bolometric luminosity of the star. And this therefore then explains why you should have the radius value, or the critical size from which you can still strip an atmosphere, moves to larger planetary sizes as you go around to more massive stars without changing anything else. Then, contrary to what you would get if you interpret these observations with photo-operation models, we find no evidence for a correlation of the underlying planet mass distribution with stellar mass. We would conclude there's no evidence for that. It could be just the same. The other interesting thing is the core-powered massless mechanism. It proceeds over gigayear timescale. So actually it means that the number of super-Earths will keep increasing with time compared to sub-Neptunes, right? The number, if you can plot this as a function of time, the number of strip cores will still go up after 100 million years, after half a gigayear, after 2 gigayears, because it's a process that's continuing today. There's actually slight evidence for that, but again, stellar ages are difficult. But that's clearly a prediction or an expectation from this. Then I think it's really important to actually self-consistently combine photo-operation models and core-powered massless models when interpreting the observations, so we don't reach the wrong conclusions. Because in some cases, they can even be the opposite. And the majority of what we currently have as rocky planets in the Kepler data is fully consistent with being stripped cores. So it doesn't prove they're all stripped cores. However, it's very suspicious to me that the only rocky planets so far that we find happen to live in this parameter space where these planets would have lost their envelopes had they had hydrogen-helium envelopes. Right? If you would find these ones in parameter space where you could not lose them, either by photoevaporation or by the core cooling, then you would be saying, well, this planet must have formed rocky for sure, because even if it had a big envelope, it would still have it today. But right now, the vast majority of rocky planets live suspiciously exactly in the parameter space where they would have lost this envelope if they had one in the past. And then my last point is that there is I think this is now a higher order thing, more compositional diversity in the exoplanet system, especially if you look at multiple planet systems, then I think I would expect by gas accretion and loss alone. And I think this is most likely a signature of collisions that happen late in the system after the gas disk is gone. And I would love to tell you about this, but I think it's probably better if I stop here and let you ask some questions. If you want to know about collisions, you can ask me about it. I'll tell you about it. But maybe I'll leave it here, and I'd rather have 7 minutes or so for questions. Thank you.
Okay, I'm sure Hilke will be willing to take some questions.
If you don't ask questions, I'm going to tell you about collisions, so you better ask questions.
Well, we'll go on here, yeah.
Mm-hmm. Yes.
So there's people listening for a class, right? So shall we repeat the question? Yeah.
Okay. So the question was whether, with the core-powered mass loss mechanism, whether we can predict what the population of planets at longer orbital periods look like. And yes, and this is something actually we're currently working on. I can't tell you the exact answer yet because one of the initial conditions changes slightly if you go to significantly longer orbital periods. We have to make sure that that doesn't change what we expect. But in theory, my naive expectation will be that you can just extend these trends to longer periods. And I think we will eventually start seeing true rocky planet analogs there in the sense that they're must have formed as rocky planets, rather than could be consistent with strip cores. But yeah, this is something that one of my grad students is currently working on.
Other questions? So what does this mean for the solar system? Are you saying that the Earth started out with this envelope, lost it, Venus did, Mars did?
Yes, thank you, because that ties to my collisions. Okay, so how does the solar system fit in, right? Like, how's it all? So I think the thing that's similar and that's different for the solar system is the following. So our terrestrial planets, right, formed through a series of giant impacts. And I think actually that most of these exoplanets did not have at least dozens or so giant impacts in their buildup, but that's a different story. And so what I think is the following. So Mars formed on a time scale, or Mars-sized embryos formed on a time scale short enough that they could have accreted some hydrogen, helium from the nebula. But because we had this assembly of giant impacts, these envelopes, if they were there, so you can just say the terrestrial planets formed so late that they didn't accrete any gas. But actually Mars is an interesting test case, and Mars would have could have been fast enough. And it's massive enough that it can hold on to hydrogen, helium, at least from the disk. So then if you have this phase of giant impacts, what we showed recently is that they are very efficient at stripping particularly hydrogen helium envelopes. So I don't have time here. In the usual impact, in the giant impact, you actually you lose sort of 30 to 40% of the atmosphere you have through sort of the shock component. However, if you have hydrogen helium envelopes, there's also a very important thermal component. You always have the thermal component, but usually it doesn't matter for the loss very much. Because hydrogen is such a light gas, what my grad student at MIT did, he showed that in this case, you get complete loss. This is the fraction of atmospheric loss. It's a mass ratio between the impact and the target. So if you look for the typical, say, moon-forming impact where you had a ratio of a tenth or so, he finds you get complete atmospheric loss easily. So I think what happens is if there was any hydrogen helium envelopes, the envelopes weren't big because you only had Mars-sized bodies. So they weren't like 1%, they were much less. But even if they were there, they were very efficiently lost sort of in the assembly of the terrestrial planets. So that's my zero-order answer to the terrestrial planets.
So you're saying that by the time Earth accreted, it had lost?
Well, so Earth accreted over a long time scale, right? But the final assembly of Earth consisted of, say, a dozen giant impacts. Mm-hmm. And even one would have been enough to erode the atmospheres between those impacting bodies. Yeah, so Mars is maybe the most interesting case because you could argue that Mars may have not had, it's really truly an embryo. It didn't have any giant impacts. And then you can ask what would have happened to that envelope for Mars in time.
And how long would have it stuck around?
Well, so you would lose it on 100 million timescales.
Okay.
But it could have observational consequences. That's something would be worth, especially from a geochemistry.
It would make it hot because it's a good thermal blanket, right? So
yeah, so
potentially.
Yes. So yeah. So there's actually something interesting there. So we started looking at that, but we haven't looked at what if there would be any testable, for example, geochemical signatures you would expect it from us that you could test that way.
Okay. Question up there.
Would there be any ice core records or geological evidence of one of these evidence ever or envelopes ever existing on Earth?
Yeah, not really, because right. So the ice core records don't go back far enough. Yeah. And then I don't expect there to be any hydrogen helium left when you had sort of the moon forming impact stages. Although some people claim you could have hid some helium or some light gas in the Earth core, but again, I think that's somewhat speculative. There's no strong evidence that the Earth had a hydrogen helium envelope, and I don't think the Earth as a fully assembled planet had that. Okay. But the embryos, so that when people do simulations of giant impacts, the terrestrial planets probably the whole region was populated by 100 or a few hundred of these smaller embryos. And they would have been large enough to just hold on to a little bit of a hydrogen helium atmosphere. But I think that was just very efficiently lost in this giant impact phase because the impacts themselves are very good. It's specifically removing hydrogen helium envelopes. It's different if you have a secondary outgas atmosphere. But for hydrogen helium, they're very good.
So it's completely eliminated with that initial impact.
Yeah, and then it just escapes into vacuum because it's, yeah. So yeah, it would be awesome to find some signatures of this, but it's probably hard because it was very easily lost.
So it's only ever going to be speculation.
For the terrestrial planets, well, we'll see. Maybe if the geochemists come up with some other really cool idea, which they keep doing, of what they can probe, maybe we can settle this question. But yeah. And some people think their terrestrial planets just formed completely in a gas-free environment. So for Earth, it's not a problem because it took a long time, right? The moon forming impact was 100 million years, roughly. But I think Mars is sort of an interesting time scale. It's just on the edge because people trying to date how long all solar nebulae stick around claim it's about 3 million years. And I think the latest claims are still that Mars formed in around 3 million years. So it's sort of maybe, but it would be easy to argue it just missed it. It's not, yeah.
But I guess, this issue about the solar system versus extrasolar systems is, you're essentially saying that the normal way for solar systems to form is through having these envelopes around rocky bodies, and then they lose them to make the rocky bodies, or they hold on to them. And so it seems a bit strange then to argue that our own solar system was in some way exceptional when it came to Earth and Venus.
I think we do not yet know if our solar system is truly exceptional, because right now what we know observationally is that half of all stars have a super-Earth or a sub-Neptune around them. So it's still possible that all of those have a solar system analogs. But we just haven't found them yet because observationally, so the reason why this phase space here is empty is because those planets, it's not that they don't exist, or they may not exist, but we don't know yet that. It's really because observationally we cannot find those systems. So we do not yet know whether the solar system is a freak, or at least the terrestrial planets are unusual or common. Observationally, we just don't know. But we will hopefully be able to answer that. Although the exoplanet missions that we have right now are not ideal for actually truly study sort of the habitable zone around sun-like stars. So, but I think there's just other modes of formation. And we know that Uranus and Neptune, this fits much more in sort of with the formation of Uranus and Neptune than sort of the true terrestrial planet analogs. But I think it's quite possible that there will be a population in our terrestrial planet regions that did form very analogous to the terrestrial planets. But right now, our exoplanet population, I don't think, is dominated by those. Yeah.
Okay, any more questions? If not, anybody who'd like to join Hilke for dinner, please make yourself known. Let's thank her once again.